Hello, my name is Bess Frerichs, and I'm a fourth-year linguistics major in the Clark Honors College. My 2025 SURF project is titled Building a Model to Predict Natural Speech Disfluencies, and I was advised mainly by Professor Melissa Redford as well as Professor Chris Kyle. To start, I'm going to play you two sets of audio, and I just want you to think of which one of these sounds more natural. Both of these are AI voices, but one of them has something that the other one doesn't.
That's a neat question. I incorporate them to make my speech sound more natural and human-like. It helps create a more conversational flow and makes the interaction feel less robotic. Plus, it can make it easier for you to follow along and feel like you're chatting with a real person.
That's a neat question. I incorporate them to make my speech sound more natural and human-like. It helps create a more conversational flow and makes the interaction feel less robotic. Plus, it can make it easier for you to follow along and feel like you're chatting with a real person.
Now, which one sounded more natural? If you're anything like me, you'd say the first one, which is generated from ChatGPT using the prompt, "Why do you, specifically, as an AI, use inhales and ums?" The second voice was generated using a text-to-speech software called Speechify. What I did was, I took ChatGPT's response and I had Speechify reproduce it. So why does the Speechify model sound less natural? I believe that's because it's missing something crucial about natural speech, inhalations, which is contributing to how unhuman-like it sounds. You can see that I transcribed all of the locations where the ChatGPT model inhaled, but the Speechify model never did this. Another aspect of spontaneous speech that can help the naturalness of it is and which are known as filled pauses. They weren't included in this example, though, because when you're talking to ChatGPT, it will occasionally throw and in, and it just happened to not in this prompt. In addition, the Speechify model would have read them out loud as well, so you wouldn't have seen this difference between the two. While the ChatGPT model is a large improvement from the Speechify model, it still falls short from sounding completely human. We argue that this is because the model is missing crucial information on where to inhale and where to say or Thus, that leads us to the goal of our study, to create a model that predicts the locations of filled pauses and inhalations in spontaneous speech. In the past, lots of research has been done on modeling the prosody of speech, which is the rhythm and intonation of speech, and the location of silent pauses within it. These models have been used to improve how natural speech synthesis models sound, but no research has been done to model the locations of filled pauses and inhalations. Our study addresses this gap. But first, let's talk about why inhalations and filled pauses are important. It's not just that they make speech sound more natural, which does help, but also because they can help with listeners' comprehension and recall. Both filled pauses and inhalations have been found to improve the ability to remember and understand what a speaker has said. Therefore, our goal is to create a statistical model of filled pauses and inhalations using logistic regression models. These models will be based on a few things: grammatical structure, such as the location within a clause, discourse structure, which is the overarching communicative organization of speech, and biological constraints of speech. Essentially, whenever we talk, we have to manage both the need to breathe with the need to communicate. We can't do both at the same time. Therefore, the longer we talk, the more air we expel, and the more our need to breathe increases. While previous research on inhalation suggests that these tend to coincide with strong grammatical or discourse boundaries, the biological need to breathe can force someone to take a quote-unquote ungrammatical breath, perhaps in the middle of a phrase or even a word. So, how are we going to build this model? Well, for the past 3-ish years, the Speech and Language Lab has been working on building a spoken language corpus, which is essentially a large collection of speech known as the Pausing Inhalation Language Structure Corpus, or PILS for short. PILS contains around 18 hours of speech, all monologic, meaning all of the speech was elicited as a monologue, so one person speaking, as opposed to a dialogue or conversation. And all spontaneous, meaning that nothing the participants said was planned or prepared in advance. We collected data from 30 kindergartners and 30 college-age adults under 2 different speech conditions. However, for the purposes of this study, we'll only be using the narrative speech, not the expository speech. The narrative speech was collected by having participants watch a short Pingu video, which is a claymation penguin. After watching, the sound on the video was muted, and the participants retold the story while the video played out a second time. All elicitations were recorded, and participants' breathing was also recorded using something called respiratory inductance plethysmography. As you can see in the picture, the participant is wearing fabric elastic bands around her chest and abdomen, and these bands are measuring the expansion and contraction of her chest and abdominal walls as she's breathing. That way, we're able to convert her breaths into a kinematic waveform. You can see what this looks like from the bottom photo. The top waveform is the breaths, where the green is the inhale and the purple is the exhale. The bottom waveform is the acoustic speech signal, or what's being said. All of the speech was transcribed and segmented into pauses and utterances, and each pause was coded with a 0 or a 1 to represent the absence or the presence of an inhalation. The picture shows a screenshot from PRA, which is a speech analysis program. You can see the transcribed speech on the second tier, which is split into pauses and utterances. Filled pauses were also coded, both in a separate tier, shown on the bottom, and in the transcription itself, using an ampersand and a hyphen. You can see that the third tier contains information from the breathing kinematics that has been transformed into a PRA text grid. To build our model, we not only need to know where these filled pauses and inhalations are in the general speech stream, but also where they are in relation to discourse and syntactic structure. Again, discourse is the conceptual organization of speech. To meet this goal, we used communication units, or C units, as they represent a complete thought. A communication unit is essentially just an independent clause and all of its modifiers, as well as other communicative phrases such as yes or no. The main chunk of what I've been doing this summer and fall is tagging the transcribed speech from pills for language structure, with the help of some other research assistants in both the Speech and Language Lab and in Chris Kyle's LCR ADS lab. This includes tagging every single word for part of speech, so your typical noun, verb, adjective, etc. What we did is we went through every single word and tagged it, then we had a model automatically tag for parts of speech as well. Any incongruencies between the human and the computer were highlighted, and then a third tagger, or the second human tagger, went through and decided which option was accurate. You can see an example of this in the first photo where you have the sentence, okay, so Pingu, he has canvas in hand. And then each word was tagged with a part of speech. So Pingu was a proper noun, he was a pronoun, has is a verb, etc. After all of the speech was tagged for part of speech, we then shifted to tagging for syntactic dependencies. So what is syntactic dependency? Well, it's a way to describe the relationship between words in a sentence where there's a root in each sentence and then every word is connected to that root, either directly or indirectly. This allows us to build a hierarchical structure of each sentence. Each word in the sentence, except for the root, has a head, which is another word in the sentence, and this is often the root itself. In the example photo, you can see the very simple sentence, and Pingu agrees, where the root is agrees, Pingu is the subject, and is a coordinating conjunction. Both Pingu and are dependents of agrees. Just like with the part of speech tagging, all syntactic dependencies were coded by a human annotator, an automatic tagger, and then discrepancies were resolved by a third tagger. Right now we are so close to being finished with the syntactic dependency tagging, and as soon as we finish, we'll be able to create the logistic regression models that will predict the location of filled pauses and inhalations. Again, this is by the syntactic structure, the discourse structure, and the biological constraints, which in this case is going to be time since last breath. This research will improve our understanding of the factors that influence the production of filled pauses and inhalations. Additionally, because we have both child and adult speech data, we'll be able to build two models, one for adult speech and one for child speech. This will provide a developmental perspective that can be used to study the development of speech-breathing coordination and filled pause production. This work also builds on my honors thesis, which I will defend in winter term. My thesis investigates filled pauses as a marker of speech planning, so these models can further elucidate the relationship between filled pauses and planning by providing more specific predictive information. Finally, this research will provide necessary information on the most natural places for speech synthesis models to inhale and produce filled pauses, which will hopefully increase their naturalness. Future research could also focus on testing the naturalness of speech synthesis models when they include these speech phenomena, filled pauses and inhalations, and when they don't. Thank you to the Speech and Language Lab and the LCR ADS Lab research teams for help with data collection and segmentation. This research was supported by an NSF grant, primary investigator Professor Melissa Redford, and the 2025 Eurocure Summer Undergraduate Research Fellowship. Here are my references, and thank you very much for listening.